All right, I have a kind of a very important video for you regarding the interference of waves in two dimensions. So we're going to start this discussion by talking about the function sine of phi, where phi is some angle. So as you're all familiar from trigonometry and other classes, this is what the sine function looks like. Now this function is important because for waves, we talked about in previous videos that a traveling sinusoidal wave is described by a function of position and time, the displacement of the medium as the wave travels through it, and that displacement function can be written as the amplitude A times the sine of kr minus omega t plus phi naught. The three terms that are inside the parentheses is what we call, or what we refer to as the phase of the wave. So every point in space at any particular moment in time has a value of the phase associated with it. So the function displacement for a wave can be written as a sine of the phase of the wave, and that phase, as we said, depends on the position and time. So the displacement of the wave as a function of phi is, as we said, a sine function. It has an amplitude A, and if I were to point to a point in this wave, like that one, and ask you what is the phase of the wave at this particular moment, well, knowing that the displacement of the medium at that point is 0 and that it is growing as a function of phi, we know that that point must have a phase of 0, because the sine of 0 is 0 and the function sine grows as you pass the point 0, the phi equals 0 point. So if I were to ask you what is the phase of the wave at that point, you can answer that it would be pi over 2, because pi over 2 is the maximum value, or is the point at which the sine function has a maximum value of 1, and therefore the amplitude with an amplitude of A gives us a displacement of A. So if I ask you what's the phase of the wave at that point, you'll answer pi, because the sine of pi is 0, and that's the point where the sine of pi beyond this point becomes negative. At that point, the phase of the wave would be 3 pi over 2. Sine of 3 pi over 2 is negative 1. And at this point, the phase will be 2 pi, or you could also say that the phase goes back to 0. 2 pi and 0 are the same angle. But for most purposes in this chapter, we're just going to continuously increase the phase of the wave without resetting it to 0. So at that point, we're going to use 2 pi. Then at this point, we are pi over 2 beyond or past 2 pi. So that would be 2 pi plus pi over 2, which gives you 5 pi over 2. And being able to identify what's the phase of the wave at different points is important, because a very key concept in this chapter is the phase difference, which we write delta phi. So for a single wave, we can talk about the phase difference between 2 points. That would mean the difference in the phase at point B minus the difference in the phase of the wave at point A. That's what we mean by delta phi AB. So looking at the values that we can identify, that we have already identified there, we have pi minus pi over 2, which gives you pi over 2. So the difference in phase between A and B is pi over 2. What about the difference in phase between A and B? Between A and C. So we know that C has a phase of 5 pi over 2, and we know that A has a phase of pi over 2. So 5 pi over 2 minus pi over 2 is 4 pi over 2, which is 2 pi. What about the difference in phase between D and A? Well, we know that the difference in phase between C and A is 2 pi, and the difference in phase between D and C must be also 2 pi. So that gives us a total of 4 pi for the difference in phase between D and A. So what we can see here is very easy to see that when a wave propagates in a medium, 2 points in the medium separated by a distance n lambda, where n is 1, 2, 3, whatever number, an integer number of lambda. So 2 points in the medium separated by an integer of lambda will have a difference in phase of a multiple of 2 pi. So if the 2 points, for example, A and D, are separated by 2 complete wavelengths, so 2 lambda, then the difference in phase between those 2 points is 2 times 2 pi, which gives you 4 pi. So every difference in distance of lambda in a wave corresponds to a difference in phase of 2 pi. What about if we're looking at waves propagating in 2 dimensions? So as we said in a previous video, if we, for example, dip a finger in a pond, we have circular waves that are propagating there. So when we represent a wave propagating in 2 dimensions, what we normally do is represent the location of the crest of the wave. So when you dip a finger in a pond, you know that the waves that are created are circular, and in this picture we're showing circles to represent the points on the surface of the water where the wave has a crest. So at that point the water level will be higher than in between them. So let's assume that at the moment when we took a picture of these waves propagating in a pond, the central point was a crest. So that means that the central point, we're going to assign it a phase of pi over 2. So the question is, what is the phase of the wave at the point indicated by the arrow? So to find that, we realize that the difference in phase between 2 crests is 2 pi, 2 adjacent crests. So between the center and the first circle, there's a difference in phase of 2 pi, another 2 pi between that first circle and the second one, another 2 pi to the third circle. So that gives us a difference in phase between the third circle and the center of the pattern would be 6 pi, and that gives us a phase for that point on the third circle as 6 pi plus pi over 2, because remember that the center we said was a crest and that had a phase of pi over 2. So if the difference in phase between the third circle and the middle point is 6 pi, then the phase of that third circle must be 6 pi plus pi over 2. So that when we subtract the phase of the center, which is pi over 2, we get a difference in phase of 6 pi. So 6 pi plus pi over 2 is 13 pi over 2. And now let's assume that we're going to generate a second set of waves in the same medium. I'm going to draw them with blue, and again the point when we took the picture of these waves, of the second set of the blue waves here, when we took the picture, the center of these circles was a crest, just like for the red waves. We're going to call this second location where the waves are produced, we're going to call it a source 2, S2 for source number 2. And the center point, as I said, just like for source number 1, we're going to assume that it's a crest and that is therefore has a phase of pi over 2. So same question can be asked here. What is the phase of wave number 2 at that point shown by the arrow? So again, we can count the distance between the center and the first circle, which is 1 lambda, which corresponds to 2 pi for the difference in phase, another 2 pi, another 2 pi. So the difference in phase between that third circle and the center is 6 pi, and when we add the pi over 2 in the middle, that gives us the net phase at the third circle to be 6 pi plus pi over 2, which again gives us 13 pi over 2. Now what about the phase at this other location? Well, that is also falling on the same circle that we calculated the phase to before. So the answer there is 13 pi over 2 also there, and also there, and anywhere on that circle. Now this point here is special because notice that at this point in time, wave number 1 and wave number 2, the red wave and the blue wave, are arriving at that point with a crest. You can see that the two crests are intersecting. So at this point, an interesting question is, what is the difference in phase for between wave number 1 and wave number 2? What is the difference in phase? So we can calculate the phase that wave number 2 has there. We can calculate the phase that wave number 1 has when it arrives there, and we can take the difference. That's what we're going to do here. So the phase that wave number 2 has there, we already calculated before, is 13 pi over 2. We're going to subtract the phase of wave number 1, but that point falls on the third red circle, and we already calculated the phase on that circle, which is 13 pi over 2. So we subtract 13 pi over 2, and that gives us a difference in phase between the red and the blue wave of 0. Difference in phase of 0. Notice that at this point we have two crests overlapping. When those two waves are arriving to that location, both waves arrive with a crest, with the highest point on the surface of the water is reaching that location at the same time. So because of that, we say that there is constructive interference at this location. Remember that, as we saw in a previous video, when two pulses arrive at the same location with the same displacement, both in this case, let's say positive displacement, they generate a bigger pulse. So there is constructive interference at that location. What about this other location? We change to here now. What about the difference in phase at this other location? So we follow the same strategy. We can count the number of wavelengths away from the center. So we have 1, 2, 3, 4 wavelengths. So the phase at that point is 4 times 2 pi. Every wavelength counts as a 2 pi difference in phase. And we add the phase of the center point, which again, we're assuming that it's a crest, so pi over 2. What about the phase at that point for wave number 2? So again, we count the number of lambdas from the center. So that's 1, 2, and 3. So 3 times 2 pi, and the center is has a phase of pi over 2, so we add that, and we get 3 times 2 pi plus pi over 2. Now we're after the difference in phase between those two waves, so we're going to subtract those two waves and two values of the phase, and the pi over 2 is going to cancel, of course, and we're getting a difference in phase of 2 pi, or if you want to be technical, minus 2 pi, but that's exactly the same difference. 2 pi or minus 2 pi are the same angle. So we get difference in phase of 2 pi. So at the previous point that we chose, we got a difference in phase of 0. At the new point, where there is a crossing of the two lines or the two circles, we got now 2 pi as a difference in phase. So for both situations, we have two crests that are overlapping, and therefore in both situations we should have constructive interference of these waves. So what can we say in general? Well, in general, if we have two waves propagating in two dimensions in a medium, then there are points which will have a difference in phase of either 0 or 2 pi, plus or minus 2 pi, plus or minus 4 pi, etc. Some of those points will be, for example, where the lines cross. These are points where there is constructive interference. You can see that the peak of one wave is on top of the peak of the other wave. So at this point, the surface of the water will have maximum amplitude. Now, something that students are usually confused about is the fact that this other point here in the middle of that square also has a difference in phase of 0 or 2 pi or 4 pi. It is also a constructive interference point right in the middle of that square. The reason why that's also constructive interference is because think about what is happening at that point. We are right in between two crests of the blue wave, and we're also right in between the two crests of the red wave. That means that we are sitting on the trough or both waves. So a trough on top of a trough also produces a constructive interference. So a trough, just like when you see two pulses in the video that we discussed before, moving towards each other, when they overlap in the middle, they just produce a bigger pulse. So at any point in a medium where there's two waves propagating, if we calculate the difference in phase at a point and we get 0 or plus or minus 2 pi or plus or minus 4 pi, we know that that point is going to have constructive interference. There will be superimpose peaks there or troughs or whatever, but the two waves are doing exactly the same thing at that moment, at that point. So these are constructive interference points. Now, what about this other point here? Notice that at the point that we're looking at right now, we're at the peak or the crest of the blue wave, and we're sitting at the trough of the red wave. So what is the difference in phase at that location? So following what we've done before, we just need to count how far we are from the center. That's 2 lambdas, which give us 2 times 2 pi phase. And we're adding the phase of the middle point, which again, we're assuming that it's a crest, which gives us a phase of pi over 2. And we're going to subtract the phase at that same point due to the red wave. So we count how many lambdas we are away from the center. That's 2.5 wavelengths. Notice that we're sitting at the trough of the red wave, so we're in between two crests, which means that that's half a lambda distance between that trough and the previous crest. So 2.5 lambda. So since 1 lambda is 2 pi and half a lambda is pi, we get 2 times 2 pi plus pi for the phase at that point. The pi came from the lambda divided by 2 distance. And again, we have to, if we assume that the center of the red waves is also a crest, to the phase at that point, we have to add the pi over 2. And when we subtract these two quantities, we get minus pi for the difference in phase at that point. So at this point, we have a crest, the blue wave, superimposed on the trough of the red wave. So what that's going to give us is destructive interference. So we have gotten, or we're looking at a point that has constructive interference, and the difference in phase at that point is minus pi. If you look at these other points, any other points like the ones that I'm showing you there, where a crest is overlapping a trough, you will find, if you look at the difference in phase, you will find that the difference in phase is an odd multiple of pi, positive or negative, but an odd multiple of pi. So at those points, every point in a medium where two waves are overlapping, if the difference in phase is an odd multiple of pi, those points will have destructive interference. You can be sure that at that point, a crest will be overlapping a trough for those waves. So to summarize a little bit what we just said, so if we have two sources of waves, S1 and S2 are producing waves, and we are sitting at some point in space wondering what's the difference in phase at this particular location. So the difference in phase is going to be determined by the distance to source number 1 and the distance to source number 2. In this discussion, we're going to assume that the S1 and S2 are in phase. Okay, so the difference in phase is going to be given by phase number 2 minus phase number 1. Now, what is the phase of wave number 2? Well, the phase is going to be a multiple of 2 pi, but what multiple? Well, it was going to depend on the ratio between R2 and lambda. If R2 was 2 wavelengths, then the phase will be 4 pi. But R2 over lambda could also be 0.5. R2 could be half a wavelength, which will give you 0.5 for R2 divided by lambda, which will give you a phase of pi, which will be destructive. So the point is that the phase with which the wave arrives at the point in space that we're looking at is going to depend on how many lambdas fit in that distance R2. 1, 2, 3, or half a lambda or a quarter lambda, whatever number that is. If you can fit 1 lambda, that translates into a difference in phase, or into a phase of 2 pi. If you fit 2 lambda, if the distance is such that it fits 2 lambda, then, as I said, the phase is 4 pi, etc. So a simple way of writing what's the phase of wave number 2 will be R2 over lambda multiplied by 2 pi. You can do the same thing for the phase due to source number 1. again, it's going to depend, that phase is going to depend on how many complete oscillations the wave can do when traveling from S1 to the point in space. So that's going to be a phase of 2 pi times r1 divided by lambda, the number of times that you can fit lambda in the distance r1. You can see that when you subtract these two quantities, you can factor out the 2 pi, you can factor out the lambda, and you get r2 minus r1. So 2 pi over lambda multiplied by r2 minus r1. This expression is valid only if S1 and S2 are in phase. Remember that in the previous discussions we assumed that they were both in phase, that they had a crest at the moment when we were analyzing things, so there was a pi over 2 phase, contribution to the phase that we subtracted for both of them, because we're looking at the difference between the two phases. The pi over 2 cancel in all cases. So when that is the case, it doesn't matter if the initial phase is pi over 2 or some different number, as long as the sources S1 and S2 are in phase, meaning they're doing exactly the same thing at all times, then what we wrote is correct. The difference in phase between the two waves, when they arrive at a common point, it would be 2 pi over lambda times delta r. This number delta r is called the difference in path length. The difference in path length. The length of the path that wave number 2 takes is r2. The length of the path that wave number 1 took to go from the source to the point in space where we're evaluating this is r1. So delta r is the difference in path length. Now, in the most general situation, you would have two waves propagating in the same medium, and to calculate the difference in phase at some point, you would use the equation that we discussed before. So according to the distance r2 from the center to the point in space, that would contribute to the phase of wave number 2 of 2 pi over lambda times r2. But the point in the middle of these red circles does not look like it's going to be a crest. That circle is a little too small to be a crest, or the distance between the center and the first circle is not big enough, it's not equal to lambda. So what that means is that that phase that we were adding of pi over 2 in previous discussions, well, that's not going to be pi over 2. So it's some unknown initial phase, which we're going to call phi 2 0 for the initial, phi 2 naught for initial phase of wave number 2. So this number right there, it's the phase due to wave number 2 when it arrives at that particular location in space that we're looking at. So the difference in phase, we're going to have to subtract the phase of wave number 1. For wave number 1, again, we can calculate the phase due to the distance r1, so 2 pi over lambda times r1. But one more time, the phase at the central point, at the center of these waves, it does not look like it's a crest. So we're going to have some additional phase that we're going to call phi 1 naught, for standing for the initial phase of wave number 1. So this is the most general situation. So what in this situation, the two sources are not synchronized with each other. Notice how the first circle is not the same size, which means that the two sources are not producing the crest synchronized with each other. There's a time difference between them. So in the most general situation, the waves arrive at a particular location in space, having been produced by two different sources that are not synchronized and having traveled a different distance. Their path lengths r1 and r2 would be different. So in the most general case, the difference in phase between those two waves can be written as 2 pi over lambda factor of r2 minus r1, which is what we call delta r, plus the difference in phase, or the difference in initial phase, that we're calling delta phi naught. Okay, so this delta phi naught, it's a number that is going to be there in every situation where the sources are not synchronized. Sometimes the problem simply says that the sources are identical or they're not identical. If the problem says that the sources are identical, that means they're synchronized. But if they're not synchronized, it probably would tell you what is the difference in the initial phase of the sources. Okay, so if the sources are not synchronized, the difference in phase will have to be calculated with the path length difference, 2 pi over lambda times delta r, but you'll have to add the difference in the initial phase of these waves. So the general equation for the difference in phase is that one. So just to give you an intuitive description of the terms here, delta phi tells you how synchronized the two waves are when they arrive at some point in space. Again, we have a medium, two waves are propagating through the medium. At any point in the medium, that point is receiving two waves simultaneously, and delta phi is going to tell us if the waves, when they arrive at that particular location in space, if those waves are synchronized or not. If that delta phi was 0 or 2 pi or 4 pi or 6 pi, we would say the waves are completely synchronized. They're doing exactly the same thing when they arrive. But if that delta phi was pi or 3 pi or 5 pi, 7, etc., we will say those waves are not synchronized. They're completely out of phase. When one wave goes up, the other one goes down, which means that they're going to destructively interfere with each other. So that's what the meaning of delta phi is. How synchronized the two waves are, it measures, it's a number that measures how synchronized the waves are. Knowing that number, we know that information. The delta r term here has to do with how much further one wave has traveled than the other wave when they arrive at that location in space. Okay, so that's what the difference in path length measures that. So how synchronized the waves arrive at some point in space, delta phi, clearly depends on how much further one wave traveled with respect to the other one. The fact that the waves travel different distances means that when they arrive, they're going to be not necessarily synchronized with each other. Then the last term tells us, the delta phi naught tells us how synchronized are the waves at the start of their journey. When the waves are produced at their corresponding sources, whether the waves are leaving their sources synchronized with each other or not. If they're not synchronized, the delta phi naught is going to be a number different from 0. So whether they start the journey synchronized or not, of course, affects whether they arrive synchronized or not. Okay, so the quantity that is going to be crucial in this chapter is delta phi, because delta phi is going to tell us whether the waves are going to interfere constructively or destructively. So to calculate that delta phi, the two terms that are important are delta r and delta phi naught. So just to summarize this a little bit more, so we have two sources producing waves. Source number 1 produces a wave. Source number 2 produces another set of waves. There's a point in space where we're standing. Let's say that we put a cork, that this is the surface of the water, and we are producing waves at two different locations, like dipping two different fingers, two people dipping their fingers in the pond, and those waves arrive at that location, and we're interested in knowing how synchronized are the waves when they arrive there. Remember that whether they're synchronized or not will tell us whether the water is going to bob, or the cork floating in the water is going to bob up and down or not move at all. So how synchronized are the waves when they arrive there? So that is the same as asking, what is delta phi? So delta phi depends on the distance that wave number 2 had to travel. It also depends on the distance that wave number 1 had to travel. And that difference in distance is what's important. It contributes to delta phi in the term 2 pi over lambda times delta r. That's how difference in distance contributes. But whether the waves arrive synchronized or not is also going to depend on whether the waves started synchronized or not. Did the waves start synchronized? If they didn't, then we're going to have to add delta phi naught. In the picture that we have here, notice that one wave seems to be starting the journey in a peak, and the other one seems to be starting in a 0. So one seems to start with a phase of 0, the other one with a phase of pi over 2. So there is a difference in phase in this picture. So we have to account for that difference in the initial phase. All right, so the key equation for this chapter is going to be delta phi equals 2 pi over lambda times delta r plus delta phi naught. And if we calculate the difference in phase and we find that it is 0, plus or minus 2 pi, plus or minus 4 pi, etc., we say that the waves arrive, or that the waves are going to interfere constructively, that the waves arrive in phase, doing the same thing. But if the delta phi is an odd multiple of pi, then we say that the two waves are going to have destructive interference, and or that the waves arrive completely out of phase. When one wave goes up, the other one goes down. All right, so that's the basic explanation for that equation. Now we're going to take a look at this situation. So again, two sources producing waves, as we discussed before. And so we're going to assume here that the difference in initial phase is 0. So it looks like the two sources in the middle, at the moment when we took this picture, they had a crest. So the middle point, the central point, is pi over 2 phase. And we're going to be looking at this point here, trying to figure out what is the difference in phase at that location. What's delta phi? So this location has a difference in path length of 0. Notice that this distance and this distance are the same because that point belongs to a line that bisects the two sources. So R1 equals R2 at any point along that line. Since R1 is equal to R2, then delta R is 0, and therefore the difference in phase is equal to 0. Again, we're assuming that delta phi naught is 0. So in our equation 2 pi over lambda times delta R, since delta R is 0, we get delta phi equals 0. True for any point on that line. Now what about this other point here? What is the difference in phase at that point? So we can do what we've done before, which is look at the distance to the center. So that's a lambda, 2 lambda, 3 lambda, 4 lambda. So that point has a distance R1 of 4 lambda. And for the second wave, we have a distance of 1, 2, 3, 4, 5 lambda. R2 is 5 lambda. Therefore, the difference delta R is 5 lambda minus 4 lambda is lambda, which tells us that at that point, we have a difference in phase of 2 pi. What about this point next to it, right there? What is the difference in phase at that point? So we can do the same thing, measure the number of the distance, which in terms of lambda is 3 of them, so 3 lambda. For source number 2, we count and we see that is 4 lambda, and that point again has a difference delta R of lambda, which gives us a difference in phase of 2 pi. So if you continue to do this at the point that I'm indicating here, you'll find that at all of those points, the difference in path length is lambda, and therefore the difference in phase is 2 pi, all of these points. Now what about a point here in between two of the points that I showed you before, right in the middle of that sort of square there? What about at that point? What is the difference in phase there? Well, again, if you do this little exercise, you'll find that the distance to source 1 is 3.5, the distance to source 2 is 4.5 lambda, and the difference one more time is lambda, which gives us a difference in phase of 2 pi one more time. So it turns out that anywhere along this line, the difference in path length is lambda, and the difference in phase is 2 pi. If you do the same exercise and figure out what is the difference in phase at these points, you'll find that it's the same as any other point along this other line, and that difference in path length is 2 lambda, and the difference in phase is therefore 4 pi. These lines are called antinodal lines. The one in the middle is the one that we first looked at. In that along that line, the delta R is 0 and the delta phi is 0. And Those lines are called antinodal lines because we have constructive interference along those lines. There is a crest on top of a crest, a trough on top of a trough, anywhere along that line. So that means that the medium, the water, for example, if this is the surface of the water, is going to oscillate with a big amplitude. If you were to put a cork in this pond at these locations, anywhere along these antinodal lines, you will find that the cork bobs up and down with maximum amplitude. Now, these three that I'm showing you here are not the only antinodal lines. Let me show you a picture that has more of them indicated. So in this setup here, we have these red lines showing you the antinodal lines. Notice that every antinodal line can be labeled by a value of delta R, that is a multiple of lambda, 0, 1 lambda, 2 lambda, 3 lambda, etc. Or it could be negative, minus lambda, minus 2 lambda. And a corresponding value of delta phi, which would be a multiple of 2 pi. So 0, 2 pi, 4 pi, 6 pi, etc. So every antinodal line, again, has a particular value for delta R and for delta phi. This antinodal line down there, you can find that delta R is minus lambda and delta phi is minus 2 pi. Now, a question that you might be wondering is, given two sources and a particular wavelength at which they vibrate, how do we know how many antinodal lines are there? Turns out that the answer to that question depends on the distance between the sources, that d distance between the two sources. The reason is that the maximum difference in phase that you will find anywhere on this plane is going to happen along the vertical line that I drew there. That difference in phase is the maximum because the difference in path length is the longest along this line. If we're sitting at a point on that line somewhere up there, and we measure the distance to source number 2, that's given by that red line, that's R1. But if we measure the distance to source number 2, that's R2, and notice that since the two sources are on the same line, the difference in distance R2 minus R1 is the same as D, and that's as big as that distance is going to be anywhere on the plane. Any other point that you choose, for example, if you choose the horizontal line that bisects the two sources, you'll find that delta R is 0 along that line. The line that has the biggest difference in path length is the line that contains the two sources. So the maximum difference in phase will be 2 pi over lambda times the distance between the sources, 2 pi over lambda times d. Just to give you an example, suppose that the distance that we chose was such that along that vertical line the difference in phase is 20 pi. So that line would be an antinodal line, but there will be another antinodal line with a difference in phase of 18 pi, and there will be another antinodal phase with a difference in phase of 16 pi, and another one at 14, 12, 10, 8, 6, etc. So that will give you, if you count them all, that would give you the answer to the question of how many antinodal lines are there. Okay, so you need to calculate, again, to answer that question, you calculate what's the maximum difference in phase. That is, calculate that difference in phase, maximum difference in phase, as 2 pi over lambda times the distance between the sources. And depending on how big that number is, you can tell how many antinodal lines you have between that number and 0. Okay, so that will tell you how many you got here, and how many antinodal lines you have above the horizontal, and then the same number will be true for below. Now there's antinodal lines along which the water or the medium oscillates a lot, but you also have nodal lines. I'm drawing one in purple. Along a nodal line, you have destructive interference. If you were to calculate the difference in path length at any point on that line, you will find that the difference in path length is half of a wavelength, lambda divided by 2, which corresponds to a difference in phase of pi. So a difference in phase of pi, as we discussed before, gives you destructive interference. So in a situation with two sources, waves coming from two sources propagating in 2 or 3 dimensions, you will have many lines along which you have constructive interference, and you will have also a bunch of lines along which you have destructive interference. Those are called nodal lines. So I'm showing you a few more here. That's not all of them. And notice that along these nodal lines, you have a peak on top of a trough. A peak of one wave superimposed to the trough of the other wave. There's some more. So you can find nodal lines, of course, right in between the antinodal lines. So for along a nodal line, if you were to put a cork on this hypothetical experiment of two sources vibrating on the surface of the water, if you were to put a cork anywhere along the nodal lines, that cork would not move. When the waves arrive at that location, they always, at all times, would destructively interfere with each other, and there will be no amplitude of the oscillation at that point. All right, that's all I wanted to tell you. Sorry for the long video. I'll see you in the next one.